Hello. In the previous video, we looked at an agent-based model that allows us to study the way a social network could influence the spread of a disease. In that video, I promised that I would also add a video that goes through the code, and that's what I'm going to do now. And so first off, let's do a little recap of what our model was supposed to do. And so here we have what we wrote down in the previous video is we have agents. They could be in three states: susceptible, infective, or removed. And they are also part of a network, and that network had a couple of properties. For instance, the degree had a number of connections that an agent could have, and there was another one that says, well, how many weak ties were there? Well, how many are there that are not connected to other people in your network? And there was sort of a probability that, a tie could be weak. The other thing is there was the disease, and the disease spreads, and the speed at which the disease spreads is covered by a number called R0, or the basic reproductive number. And the properties of our network, so the basic reproductive number is sort of the potential of spreading, and the properties of our network limited that whether or not we could reach that potential. And, we actually like it if it didn't reach that potential. And so that's the R0, and then we had a duration of the disease, and those are all settings of a model that we could play around with. And so that's one of the things that we want to do in our code, is to allow the user to set those settings and to easily change those settings and to play around with them, because that kind of experimentation is what an agent-based model is all about. Okay, and then there was a rule for each agent, and particular each infective agent. Each day, each tick, each time unit, all infective agents look at their neighbors, and with a chance p, they infect them. And that chance p basically comes forward out of those the degree, the duration of the disease, and that governs the number of opportunities an infective agent has to infect them, and the R0, what the end result of all those opportunities should be if they were all susceptible. Right, so from that comes the number p, the chance that you get infected. Okay, so how do we put that into code? So here we have the code that I use to create those graphs. It's done in Stata, so if you want to run along with these models, you'll need Stata. And in particular, what I'm using most of the time is its matrix language called Meta. And what I'm doing is I'm first creating an instance of a class called COVID. So a class is a big container of data and functions, and I created that here. So we'll get to that. And then once we created that instance, we set the settings, and that's what we can see here. We set the number of nodes, the degree, the probability of a weak tie, the basic reproductive number, and so on. Once we set the settings, we run the model, and we export the results to Stata. And in particular, we are storing something called the network. Okay, so that tells us something, but actually not a lot of what we're actually doing. And here we have that COVID.meta that created that COVID class. And as I said, it was a big container. It is a big container of data, and that's what we have here, and functions. And so, well, some of the functions we have already seen, right? These were the functions that set the settings. And what they do is, if you specify a value here, they get stored in this scalar here. The other thing it can do, if you don't specify any value here, it will return whatever you stored in this particular scalar. Okay. So there are, whether or not it returns something depends on whether or not you set a value here. So um, it doesn't tell you beforehand, it's transmorphic, it doesn't tell beforehand whether it will return something or what it will return. Right. Then there are a couple of functions that do some checking. So if we set the number of nodes, then the number of nodes has to be a positive integer. And that's what the function isPosInt does. And the same is a probability does checks whether or not a value is between 0 and 1. The next thing we saw is that we ran run. And run actually runs the model. So it first runs setup, it does some checks on your settings and sets defaults if they weren't set, and then it creates the network. And then at each point in time, it lets all infective agents look at their neighbors and infect them if necessary. Hey, look at all the neighbors, and if necessary, infect them. And then you need to copy at the end of each time the results to the next iteration, next time date, next day. Once you're done running, you can export your results to a state, and that's what these functions are for. So let's look at a couple of these functions. We have our not. That's a function, so there are parentheses around here. There's a bar here that says, well, there you can have arguments, but you don't have to. And as I said, it's transmorphic. We don't know what it's going to return. And it's part of the COVID class. And that's what COVID and these two columns mean. Now, if you specify one argument, if you specify a value, then we set our not to that value. And we first check if it's negative, and you can't have a negative R not, so you get an error in that case. If you don't specify a value here, then you specify 0 arguments, and then you come in the else block, and then you return whatever R not and this scalar is. And the other settings functions work in pretty much the same way. And they're transmorphic. You can set a value, but you don't have to. They're part of the COVID class. If you set a value, then you set the value, and otherwise you return the value. And that's the basic structure here. And here are the check functions. You give them a number. And so here we see if you specify the datum, it has to be a positive integer. And what you do, you give it a value, and then it checks if it's a positive integer. And if that's not the case, it will return an error message. And the same for isPer. So then the next step is basically you do a setup. And this is part of the run function. It's called by the run function. It clears the network, it checks whether or not all the settings are there, and either returns an error message or it sets some defaults. And then it works on the network. And the network, well, actually is a class of its own, and we can see that. Now, all the way at the top, where is network? Here's network. It's a class of type ABM network NW, and well, it's a scalar. And so there's one instance of that particular class. It comes from here. There's a GitHub repository for this particular class. It's there to help you manage a network in an agent-based model, which is exactly what we're trying to do here. It contains functions, it stores that network and allows you to access it. And so that's what we're trying to do in setup. And so we cleared the network, And now we're setting properties of the network. It's not a directed network, so A and B are connected. It doesn't matter whether A connects to B or B connects to A. The direction doesn't matter, just A and B are connected or not. It's not weighted, and there's no weight on these connections. And then we wanted to create that circular network with a few long distance ties, and we do that with the function SW, which stands for small world, and the arguments are the degree and the probability. And there's the chance, which here are called W, of that when you look at the neighbor, whether or not you will affect it. And that was a function of the basic reproductive number, the duration of the disease, and the degree. And then we set up a number of functions, a number of variables that allows us to track the progression of the disease. So here we have the number of infectives that at each point in time stores how many people are infected. And here, cumulative effective at each point in time, it stores how many ever got infected up till that point in time. Here, for each person, it stores how many people did you infect, and that's the actual reproductive number. And we saw that the properties of the network allowed us to really reduce that reproductive number compared to that potential of the basic reproductive number. T start for each person, it records when did it start to become sick. The duration for each person and each point in time, it stores how long you are sick. And so this allows you to get well again, right? Because after well, what I said, 5 days, you got well again. Susceptible for each person and for each point in time, the 0, 1 variable, yes, no, whether or not you're susceptible. And the infectives is for each point in time a list of the number of people who are infective, and that's variable how long that list is going to be. So we don't do here a matrix, but a so-called vector of pointers. And we start with null pointers, and here we fill those null pointers with, and here we point to, let's call it a bookmark, to a empty vector, and later we'll fill them up. And then we, for the first number of index patients, that was one of the settings, we infect them. There's a function called infect. And here we have that in infect function, and all it does say, if you're susceptible, you're giving it a time and an ID. If that person is susceptible, then you set infectives at time t, and that's the list of people who are infective, is the old list of infectives, and you add the ID to that at the end. So the first people in this list are the oldest or the longest infected. And once you have that, you create a bookmark, and that's what the ampersand is, to that new list. The duration for that person that got infected at that time is set to 1. At that point, you're no longer susceptible. You already have the disease. The number of infectives goes up by 1. The cumulative number of infective also goes up by 1. And in T start for this person starts at, you start becoming sick at this time. And so being infective just means that a lot of these variables are set to different values. Okay. Now, and so setup calls infect neighbors. And so at each subsequent period of time, we're going to call infect neighbors. And so this is a person that's infective at time t. At first, it looks at all its neighbors. That's a function that's part of the ABM network class called neighbors. And we're saying this is the ID. Time here is 0 because the network itself remains constant. The only thing that's changing are the properties of the agents, whether or not they are infected or not, or healed. And so the network actually has a TDIM of 0. And then we want it fast. So it gives me a list of the neighbors, which we call calls. And then we loop over those neighbors, and with a chance of W, we're infecting them. And we're also storing whether this agent, the number of people it infects, we store that in the vector called R. Right. Well, which function calls infect neighbors? Well, that is step. And so step first starts in infecting neighbors and then starts healing neighbors. And so first we get a list of infectives at time t, and then we store the number of people who are infective at time t, and we have a scalar j that we set to 1. We'll loop over them, and if they aren't healed, if their duration is increased by 1, and if that duration doesn't exceed the duration of the disease, then they can infect their neighbors. If they are healed, then we increase the scalar j by 1. And that's the end of the infection. So the scalar j at the end of this loop counts the number of people who are healed plus 1. And since we stored the number of infectives such that the oldest are first, we can use that to heal them. And so now here we get the new list of infectives, new number of infectives, and if J had the number of people who are healed plus 1, and there is someone who gets healed and it's less than the number of infectives overall, then we're just removing the first J minus 1 from the list. And if everybody got removed, then we set it to an empty vector. Now, once we do that, we also need to change the number of infectives at time t. And we subtract the number of people who are healed. We're infecting at a given point in time, we're healing at a given point in time, and now copy props moves the state of the network to the next point in time, so we can change it in the next point in time. We'll start over there. And if we don't say quietly, then we get some output of what day it is, the number of infectives, and so on. And copy props, this copies as susceptible for t plus 1, gets susceptible of t, and so on. And what we actually saw at the network thing, we set the settings and then we ran run. We didn't see step or anything of the others. Well, that's what we see here. It's just we run setup, and then for all the time points, we run step. The step is this one. And after that, we have a couple of functions to basically export whatever we have in our class to Stata. And so this is the basics of the code that I use to create this agent-based model. And it's on GitHub. So by all means, play around with it and um, have fun with it. Okay, bye-bye.